absolutely amazing. It will change your life. Okay? Are you ready? Suppose we have a curve, and we're going to take that curve, f of x, and we're going to revolve it around the y-axis. Immediately, what you think about is using washers in order to find this volume. Okay, all right, Brody wants to use a cone, and he's going to get it wrong. So don't draw this, but I'll show you the washer deal. I draw a washer, and you're feeling pretty good because you're like, Mr. Gibbs taught me how to do the washer thing, and I get it now because I practice. I use my workday very wisely, except if my name's Joe Peterson. I just chose not to show up, so. But that's all right. You know. So how's that? You like the washer? We good? So tell me why I can't do it. What makes up big R? What makes up little r? Same function. You multiply. You square it. Yeah, is zero. Zero's the answer, right? We're done. No. You guys like that, huh? Just write a bunch of zeros on the board. You like the zero, huh? Yeah. Let's do it. You got a five there. Okay. All right, you can be proud of that. Let's see if you still have that at the end of the day. All right. You're just a negative zero. You don't belong in this class. Okay, so here's what I'm going to do instead. Prove there's negative zero. You guys are so dumb. All right, so we've got a vertical rectangle, and what's the thickness of that vertical rectangle? Very good. It's dx. Okay, it's got a horizontal thickness. Now here's what I'm going to do. I'm going to take just that rectangle, that small little segment, that infinitely small segment, and I'm going to rotate it around the x-axis over here, or the y-axis over here. And when I rotate it over there, I get this shell. It's have you ever fired a gun here before? Or has you ever fired a gun before? Okay, so when you fire a gun, you gotta remove that shell afterwards, right? Hide, hide the evidence. Um, it's very thin, but it is that shell, or like say the label of a soup can. That's what we've got, and there's a whole bunch of them. Like somebody said, well, why did you draw the rectangle there? You can draw it here and rotate that thing around over here, and sure enough, you've got you know you've got another cylindrical shell going on. Have you ever seen those Christmas dolls that are made out of wood that stack inside of each other? Yeah, they're the Russian ones. That's exactly what we got going on here. It's the same type of thing. Just all these shells, they just stack inside of each other, and that will form the entire volume of the solid. How many shells do we want eventually? We want an infinite number. We have three right here. You can see how they stack inside of each other. you can see if we drew rectangle next to rectangle next to rectangle next to rectangle, we could draw all those cylindrical shells. Now the question is, how do we find the volume of one of them? Well, if I were to take that shell and unravel it, what shape would I get? A rectangle that has a thickness, an infinitely small thickness that we call dx. Well, here's the cool part. The height of that rectangle is going to be the same as the height of the function. And then, if we unraveled that soup can or unraveled that cylindrical shell, how would we determine the length of it? 2 pi r. That's the same as circumference. If that's A and that's B, then the radius just happens to be whatever x value we evaluated that height at. So look at this. If you're evaluating the height at x, what's the distance from x to 0? It's just x. So therefore, the radius in this situation is often x. So it becomes 2 pi times x. We multiply all three of those dimensions together, and we get 2 pi times x times f of x times dx. And that represents the volume of one of those shells. Amen, brother. Slap the integral in front of there, because then we've got an infinite number of those shells. We integrate a to b, and it's x times f of x dx. And just a point of caution, x refers to the radius, and this often does change. Okay, this is just a general formula. Ready for an example? We do 3 examples. We get through all 3. You got work day tomorrow. Let's do what's easy. 2x squared minus x cubed. What does that graph look like? Looks like that? Very good. So he factors out the x squared. He's got 2 minus x, double root at 0, single root at 2. And we're just going to draw this portion of the graph because it's also bounded by y equals 0, which is that x-axis. Yep. Where are we going to revolve that around? The y-axis, so I get the same shape going on over there. Hey, no big deal. Let's just do washers, right? Why? Same inside as outside. So therefore, what we do is we draw a vertical rectangle. We say, well, maybe let's try doing a cylindrical shell option, see if that works. Here's well, talking about Isaac Newton. Okay, here's the amazing thing. Okay, we're not limited to washers or to shells. They're just the shapes that come up most often. Anything that you can find the area of, you could use in order to determine this. You just got to come up that. All right, so I'm going to unravel that shape. What's the width? What's the height? Which is 2x squared minus x cubed. That's the function, right? That'll give me the height. How do I determine the length? What? This is the shell unraveled. It's like I took it, I cut it somewhere and unraveled it and set it over there. cut it right here, unravel it, throw it over the side there. So that's what we're finding the volume of. Okay, so I've got a bound from 0 to 2, and we chose an x value. What's the distance from x to 0? It's x. So therefore, we have 2 pi x. So the volume of one of these, is 2 pi times x times 2x squared minus x cubed times dx. I take all those things and multiply them together, and that's what I get. Yep, infinite number, that's what we do when we get back. All right, here we go. This is our integral. Now, the nice thing about this is compared to washers, you don't have to square anything. So you really, a lot of times you avoid a messy integral. We get 2 pi times the integral from 0 to 2, and you just distribute the x, you get 2x cubed minus x to the fourth dx. So really the only thing that happens when you do the cylindrical shell method is just distribute that x. Antiderivative of 2x to the third. Yep, x to the fourth over 2 minus x to the fifth over 5. Evaluate 2 and 0. Plug in 2 to the fourth. What is 2 to the fourth? 16 divided by 2. And that will be 40 over 5. 8 is 40 over 5. Plug in 2 to the fifth is 32. 32 over 5. Okay, 8. Oh, 16 pi over 5. For cylindrical shells? Yes. This would be more of a level 3. We'll do 2 next. So. Okay. Obviously, you guys know by now that the most challenging part of these problems is the setup, isn't it? Okay, drawing the graph. Y equals x minus x squared. You should all know what that looks like. So tell me. That goes through 0 and 1. Thank you. So you factor out the x, you get 1 minus x. So we go through 0 and 1. So we've just got this part. Since this is also bounded by y equals 0, we got this section right there. That's my region. I'm trying to find the area of, and then I'm going to revolve that around. Ooh, revolving around x equals 2. That's different, isn't it? So would you agree that my bounds are going to be from 0 to 1? You always determine your bounds by your original area. Revolve that around the line x equals 2. I get a shape over there. I'm going to draw a vertical rectangle that is thickness of what? Dx. And as I revolve that around, this one for me is I think I added this one 2 years ago. It's very challenging. It's one of the most challenging parts as a teacher when you're teaching this challenging type of content is what level of problem is ready or the kids ready for. So like as I'm doing it, I'm like, okay, well now I can do this, this, or this. But you realize after a while, oh, the students need to see this type of example, and that's the challenging part. So, but now this is gonna be good, and this is a great example. You guys are gonna connect your learning very well here. But yeah, it took me a while to come up with it. Okay, so I get a cylindrical shell. I'm going to unravel it. Yeah, what's the thickness of that rectangle? It's dx. Okay, so again, we have it's a rectangle that has just a very small width, infinitely small width. What's the height of that rectangle? Yeah, and then the length of the rectangle, 2 pi r. And the question is now we have to find the radius, and this is where it's just slightly more delicate. Because would you agree that this blue line represents the radius? So suppose that this location there was 0.5. You might choose x to be your radius, but 0.5 is not that radius, is it? What is the radius? 1.5. You took 2 minus x. It's always the right minus the left, or the top minus the bottom. Look at how that's consistent with what we did in the previous problem. Here, you evaluated it at x, you did x minus 0, and that distance was x. Well, same thing here. When you do the right minus the left, right is 2, left is x, so the radius is 2 minus x. So that's tricky. Yeah, so when I multiply all this out, I have 2 pi. I have 2 minus x. I have x minus x squared. And I have dx. Yep, that's one. Just one of those cylindrical shells. Doing infinite numbers, so put that integral. In order to determine my bounds, I always look at the original area. 0 to 1. You can put 2 pi on the inside if you want. I like to leave those constants out front. Just keeps the problem cleaner in my opinion. But it's a free country. Do what you want. Now let's multiply all that out. So we got positive x cubed. And minus 3x squared. I think I got a plus 2x on that. Let's take that antiderivative. Antiderivative x to the third, x to the fourth over 4. Antiderivative negative 3x squared. And antiderivative x 2x's. Hopefully you can also appreciate that when I wrote the problem, having the bounds of 0 and 1 is rather nice, isn't it? It's always nice plugging 0 and 1. I have to applaud the AP exam as well, or compliment them. As they write the problems, they often will choose bounds or situations that work out quite nicely. So you plug in 1 and you get 1/4 minus 1 plus 1. 2 pi times 1/4, which is pi over 2, or 90 degrees. Right? So I'm really glad that you guys respond that way, because second hour, most people just wrote down the 90 degrees, nodded their heads. So, guys, come on. A few of them sat there kind of snickered. They're like, that's dumb. So anyway, all right, let's do the last one. As we move to the last one, I would like you to just glance at the board, though, and there comes a point where you have to feel slightly impressed that you're capable of handling that type of a math problem. I mean, if you look at the beginning and look at what you're asked to do, find the volume, this revolved around that. Okay, at the beginning of class, you had no idea how to do it. It does. You would have tried a washer method and would have failed. 2 weeks ago, you wouldn't have even known how to try a washer method. you just would have wondered, where do you even start? But the beauty of calculus is this. Okay, really makes it pretty cool. Okay, let's do the last one. I love this last example. I used to not include it, but this is a great example because it shows us how you can use the cylindrical method even if you don't have to. Okay, let's look at it. We've got x squared and y equals x. Everybody agree that that's where those two kind of cross? And we're going to revolve that around the x-axis. So that's different now, isn't it? No, no, it's not. So no. So you're looking at this original area, which is positive, and you're revolving that around to collect more of a solid. So you're right. If we had area that's at above and below, then that would cancel each other out. That's definitely not what we have because we're revolving everything. Okay. Yes, assuming it's symmetrical. So this is what I have. Now, what's interesting here is I have a different rotation. I want you to consider this. Could I do a washer method here? Why? Different top and different bottom. So on the test, or yeah, on the test, you could set up this problem using the washer. And a lot of people say, well, they want to use the washers. Um, there's no reason why you can't use the cylindrical shell method, and it's just as easy. Might even be easier. I'll show you the cylindrical shell method right here. The difference is for cylindrical shell is as you do the shell, what's your thickness? It's dy. Oh boy, wow. Ouchie. Maybe. All right, we've got this. Okay, now it's time to, we're going to unravel it. We said that the thickness was dy. This is the most challenging part for people to see is what is this dimension right here? It's x squared minus x. It's the right minus the left in order to come up with that distance. Except it's not. Why? Because you have to go in terms of y. Very good. So you got y, and this will be the root of y, right? Root of y minus y. Root of y minus y. Yeah, so you had the right idea. Exactly. We can't leave as x squared minus x. Paying a dime with two nickels, yes. Well, I have y equals x squared. So if I square root both sides, then I get x is equal to the root of y. And then here, y is just equal to x. So x equals y. So I take the root of y minus y then. Okay, how about the height? This is going to be 2 pi r, correct? We just have to find r. Well, my bounds of integration, anybody know where that intersection point is? Yep, so 1, 0, just make a good guess. And so we're going to choose a y value that sits between 0 and 1. So that's simply just any y value that we choose. So therefore, our circumference is 2 pi times y. Our radius is y. Okay, so what is the volume then of this one shape? 2 pi times y times root of y minus y times dy. That's 1. Infinite. So we go 0 to 1. We distribute it through 2 pi. What's y times the root of y? Y to 3 halves minus y squared dy. 0 to 1. 2 pi. Antiderivative of y to the 3 halves. Y to the 5 halves divided by 5 halves or multiplied by 2/5. Okay. All right. And then minus y cubed over 3. Evaluate that. 1 and 0. 2 pi times, looks like 15 is going to be your common denominator. You plug in 1, you get 2 over 5, which is 6 over 15. Very good. Minus, you plug in 1 here, we get 1 over 3, which is 5 over 15. Very good. And so you get 1/15 times 2 pi. 2 pi over 15 is going to be that volume. Now, again, I want to be clear. Same problem, you could use the washer method. So cylindrical shells they're a nice option. They really are. What? Um, Carter had a good question, and his question was, suppose I take this shape and I were to revolve it around this axis. Could I use the cylindrical shell method, or would I have to use the washer method? And that's a really good question. You technically really can't use the cylindrical shell method here, because if you look, if you were to draw it like this, you would have the same right as you do left, correct? So in that situation, you would definitely want to use the washers. You have a different top and different bottom. Other ways to work around this, and one trick we never really talked about, is that, well, instead of going right to left using the same function, you could just cut it in half and then double it if you wanted to, if it was symmetrical about the y-axis, but that's not always the case. So there are ways to manipulate functions mathematically in order to create better shapes in order to work with, but I would discourage you from doing that unless you feel really, really confident. You can't. I mean, this. No,